Welcome and good afternoon. I'm Don McPherson here from Hydrocomp, but today I'm just the MC for our own Adam Kaplan, who's also the CTO of TrueProp Software, our sister company, on this webinar on propeller inspection, exposing the good, the bad, and the ugly. Just a reminder, we'll be attending to questions after the presentation is over. Please send Adam any questions that you've got through the chat feature on the side. And when the presentation is over, if we have some time, we'll be able to address a couple of those questions. So with that, let me hand it off to Adam.
Hello, everyone. Thank you all for attending today. I'd like to welcome everyone to our first TrueProp webinar, first of many, hopefully. This webinar is not a software demo, so we want to start discussing some nuanced topics and share our knowledge with you. Don's going to take notes of the questions during the presentation, and we're going to address them after the slides. So without further ado, let's progress into it. Propellers are the unsung driver for a large part of our economy. There's over 12 million registered boats in the U.S. alone, and propellers directly affect vessel performance, fuel consumption, and emissions. So this means that propellers require periodic inspection, maintenance, and repair. And of course, even the best watermen have propeller strikes, whether it's a rocky bottom or a log or a rope. It's common for propellers to get damaged. And we hope that this presentation will be valuable to repair shops, naval architects, boaters, and we hope to answer three main questions during the course of this webinar. When do propellers need inspection? How can propellers be inspected? And what do the inspection results mean? The first thing we need to accept is that all propellers have blade-to-blade variation, and this means new propellers, hand-ground propellers, and even fully CNC machine propellers like you see on the right here. There are slight differences between each blade, and any variation between these blades affects performance. And how does it affect performance? You can have issues with vibration and noise coming from the propeller and being noticeable on the rest of the boat. It could be bad for bearings and engines and all that as well. You'll have speed and thrust performance issues to worry about. So you can see loss in speed or loss in thrust due to variations in the blades, and we'll discuss that a little bit later. And you can also see increases in power requirements, essentially kind of blades fighting each other or not being optimal, damage to the edges or the tip, reduce the efficiency of the propeller and increase the power requirement. So how much variance between the blades is tolerable? This may depend on the propeller style and the type of vessel. Obviously, a workboat and a motor yacht are going to have different needs as far as the tolerances go. Many propeller inspection facilities and repair shops are using a manufacturing-based geometric tolerance for guidance. This set of guidelines or criteria is put out by the International Standards Organization and is called ISO 484. Now, ISO 484 is not explicitly meant for repair. It's meant for manufacturers to have a way to quantify their dimensional tolerances for new propellers, but it's been deemed a fair criteria for tuning and repairing propellers back to kind of as new or better than new condition. ISO 484 gives us 4 different class ratings, and these classes are increasingly tighter and restrictive. So at we have wide tolerances or a class 3 rating. And then we would progress to a class 2, which they are describing as a medium accuracy. Class 1 is a high accuracy and class S is a very high accuracy. And what you can see over here is the tolerance value, the percent deviation that's allowed with each class changes. So as we go from class 3 to class S, our tolerance tightens up from plus minus 3% to plus minus 0.5%. Now we'll discuss what this tolerance and measurement is related to, but what you'll generally see in propeller inspection reports, modern ones anyway, is that we can represent that measured value against this tolerance. So we have our target measurement of what it should be, and then we have the variation about this target. So how much variation is tolerable? We have this tolerance we can set, and so if we are inside this window, we're considering that to meet that class rating, that criteria. Now, the propeller is a wear part. It's an external, mostly unprotected component on the ship. Corrosion, cavitation, abrasion naturally wear down the propeller over time, even without damage or contact with anything. So a propeller's lifespan is limited. At some point, props can be damaged beyond repair, or and then they'll need to be replaced. Now, repair shops are incredibly talented. They could probably fix anything that had a hub intact. But repair costs versus replacement costs need to be considered within the context of the propeller's lifespan. If it's already been reconditioned a few times, perhaps it's ready for being replaced. Every time it's reconditioned, that removes material from the blade surface, and every time the propeller blades are bent, we start to approach the metallurgical limits of the material themselves. And then we're also welding material onto the edges. We're filling in cavitation burns. So at some point, the propeller is going to reach the end of its lifespan. Now, inspection reports can really help you source replacements, and so it's good to document what you have early on before it's gone through a series of repairs and adjustments, so that you can find replacements in the future. This picture on the right is from a propeller shop in India, and they had this sitting right in the front of their lobby there, and they were basically demonstrating that they could fix, even a blade that had been tulipped over there. Now, they wouldn't actually go and fix this, but it was just a demonstration of their capabilities. Very talented, these people. Now, when to inspect a propeller is another question. Usually a brand new propeller, an OEM, original equipment manufacturer, will actually include a quality certificate or a report with a new propeller. That same quality certificate may actually be generated by the reseller or the propeller shop selling you the propeller. So, you may get that in a higher end prop. Now, even if you don't get that report, maybe you should request it if you're a boat owner or an operator or a shipyard naval architect, because there are many benefits for having this documentation. First, obviously, it documents the current condition of the propeller as it leaves the shop before it goes on the boat, so that you, one, have something to restore that back to in the case of a strike. But you can also get a propeller, and if it's going on a high-end application, perhaps it needs to be dialed in just a little bit further from what the manufacturer had. Some manufacturers would provide maybe a Class 2 propeller. Maybe a motor yacht wants a Class 1 or a Class S, so they can go and tune that propeller to improve it. Now, the major reason for this, and we encounter this a lot in our work with Hydrocomp, is performance troubleshooting. So a boat that maybe got a new engine, they go out for a sea trial, they don't quite make speed. And so now we have to go and model this up. And the first question is, what does the propeller look like? What's the model, blade area, number of blades, pitch, diameter? So documenting that with a report is invaluable to repair shops, naval architects, and others who are trying to do before and after changes to dial in different boats. And of course, we talked about sourcing replacements already. So eventually that prop will wear out. All that work you've done to dial in the boat, it's best to have, you can find the best, most appropriate replacement propeller for yourself. Let's talk about how propellers are inspected. Now, in the early days, propeller designs were largely simple. The blades were a flat face, constant pitch design, and these had relatively large tolerances because there were no CNC machines manufacturing these. These were all the handmade molds and poured and hand ground to be finished, so they had large tolerances. To measure these blades, they built these large radial measurement machines. We call them pitchometers, but these were essentially drop rod scales. And you can see one down here. This is from 1942, but the pitchometer was actually built in the early 1900s, like 1907 or something like that. And that's a visual scale that drops down, and you actually read the tick marks off the scale to get the drop value. And so the operator had to he had to go and lay out manually on the blade where he was going to take his drop point readings. And depending on what class or tolerance he needed, he would lay those points out differently. And then he would visually use this scale to take readings, record them down, do his calculations. So they were relatively crude devices, manual movement, and required the operator to actually interpret what was going on. Now, as we progressed, now we're into basically the late 70s and early 80s and late 80s. Propellers began to be developed more commonly with foil shapes than flat faces. We began to see variations in pitch. And when we say variable pitch, we are not talking about controllable pitch, detachable blades from a hub. We're just talking about propellers that had a pitch distribution that was changing from the root of the blade up to the tip to kind of better match the water flow. And so these were harder to inspect. So they developed in 1981, the ISO 484 criteria was released, and later in 1987, NAVC, which was working with the Navy to inspect their propellers, also established their own inspection method that used visual gauges. And that's what we're seeing here. These are, on the left here, we're seeing gauges for the edges of the blade. And so these would go on the edge. You could rock these gauges back and forth to check the upper and lower surfaces of the edge, the nose radius, and you could visually say, yes, it's in tolerance, no, it's not. And similarly, they had cylindrical gauges that went around here. So these gauges, they would develop a set of gauges, and those would be used for the same propeller on multiple ships, which made sense for the Navy. So the Navy could keep a set of gauges, and they could use those for those sets of propellers, and that's how it worked for them. Now, gauges are typically made by a propeller manufacturer as opposed to repair shops, but they're still used to repair high value propellers, and the Navy still uses them to this day. So just another way that propellers can be inspected here. Now, with the rise of computing in the early 90s came the first computer-assisted inspection devices. So as digital pickups or encoders, as they're called, and digital readout systems became more affordable, it became possible to retrofit those simple drop rod systems with kind of digital electronics. And there's several benefits to that. The first is that you have increased accuracy. The electronics actually have more measurement positions than looking at a visual tape measure. They just are finer. You can get down to thousandths, 5 thousandths, 10 thousandths, a single thousandth, versus dealing in 16ths of an inch. So that eliminates the visual interpretation of the measurements right there. The readout gives you the number. As we progressed further, there became the computer-based systems that we're familiar with today, which they further automate the data acquisition process. And then instead of just recording the data to the computer, they supplement it with analytical capabilities and reporting. So the ability to evaluate whether things are within those tolerances and then generate a report out. So the use of these digital systems enables rapid, near continuous data sampling so that you can actually trace the surface of the blade. And we're going to see an example of that next here. So This is on the left, we're seeing, well, both of these are from TrueProp software, but this is the data that we capture from the surface of the propeller. So we are looking down above the propeller, down at each blade. Each blade is shown in different color here. And each of these lines, if we look at the blue blade number 1, each of these lines represents a line that the operator traced across the blade surface. So as they sweep over from this trailing edge to the leading edge, the angle is changing, but also the drop is changing. So the trailing edge is higher up, the leading edge is lower down, and we're seeing these paths here for each of these lines. And from these paths, we can calculate the angle, and then we can compare the angle between the blades. So this digital data capture kind of separates the data acquisition from the analysis. Now we can go back and add, we can check this in as many or as few positions as we want, and we don't have to go lay out our blade all over again. So what's the objective of inspecting this propeller? What do these inspection results mean? Well, all of these methods we've seen earlier, they're all seeking to quantify the propeller's pitch. And propeller pitch is an essential tool for repair shops and for anyone working in naval engineering for correcting a vessel's performance. Dialing in the pitch value is very important to getting your engine loads right. So pitch is a geometric measure of the angle of the propeller blade. It's one of the most critical aspects of a propeller's performance. So you think about driving down the road, your hand out the window on a hot summer day. If your hand's flat, you only feel resistance. And as you angle your hand higher, you're going to feel more and more force. And this is kind of the lift force here. So if you think about varying that angle of your hand, like variation between blade to blade to blade, you can see those forces are going to be different on each blade, and that can lead to the vibration and the noise that we've talked about earlier. But unlike our hand out the window, the propeller blade is attached to a rotating hub, and it's rotating through the water. So if we rotate it fully, we get this theoretical distance of advantage, and that is the pitch value that we're quantifying. So pitch is one of the few parameters that boat owners regularly encounter, and that's why it's probably the most prominently focused in the report. It is very important to performance, but boat owners also understand this. When they purchase a propeller, they're going to purchase it in a specific diameter and pitch, and so the overall propeller pitch is very important, and tuning that allows them to figure out where they need to go up or down. Or sorry, inspecting that allows them to figure out whether they're going up and down. And to kind of show how this happens in practice, here is a vessel with 3 different propellers. They're all 18.5 inches. One on the left here is a 26-inch propeller, and you can see now the engine's overloaded. And on the far right, we have a low pitch propeller, an 18.5 by 15, and you can see they're only getting 17.2 knots, and they're only using about half their engine power. But when we dial this into an 18.5 by 20, we're hitting 22.7 knots. And there's one big thing to take away from this, and that is propeller inspection is about what your propeller is, not what it should be. When we go and measure it, we are figuring out what that number currently is. And then from there, we can make changes to improve the vessel's performance. But we need to know what that number is. And then we can go and address the problem, which is a completely separate problem about what that number should be. So this means you can have absolutely a perfect Class S propeller that is exactly perfectly wrong for your boat. Let's dig a little deeper into how we come up with that propeller pitch value. The overall pitch value is really important, but it is actually an average of the blade pitch values. So if you have 4 blades, we have 4 separate pitch values for each blade. And we average these to come up with the propeller pitch. So let's say the overall propeller pitch is 24, and that's exactly what we want. So that's good. But if we look a little deeper, we see that blade 1 and blade 3, they're both 24 inches. We have blade 2, which is 22, and we have blade 4, which is 26. So we have a high blade and a low blade and 2 blades that are good. The average comes out great. It's still a 24, and the propeller is going to essentially act like a 24. But what we are seeing is that these blades are outside their tolerances. You can see blade 4 is above the maximum tolerance limit, and blade 2 is below. So we're using this window and these bar graphs again to represent that. And now that we can see that these two are out, even though this propeller's a 24-inch propeller, and it may perform like that, it may have noise, vibration issues, it may have added inefficiency as well. If we go another layer deeper, there's multiple measurements that are integrated to calculate that blade pitch value. So on the previous screen, we had blade 1 with a pitch value of 24. How do we come up with that? We averaged, oops, sorry about that. We averaged the value of each of these individual scan lines that we took. So we went from the leading edge and we did them 30%, 40%, all the way out to the tip of the blade. We had our 8 measurements and we averaged those together to come up with an average for that blade. And we repeat for each blade. Now, similarly, that blade pitch, that blade 1 can be a 24-inch pitch and be in tolerance, but maybe these individual radii may be out of tolerance. So we visualize that with more bar graphs. This is a 3-blade outboard propeller, and so you'll see the value for each blade. Blade 1 is in blue, blade 2 is in purple, blade 3 in green, and this is the innermost radius here, the 50%. So it'd be kind of pretty close to the hub here, 60%, 70, 80, 90, 95, all the way out to the tip here. And to get the value for each blade, we average the value from each of these radii together. So we take the blue bar from the 50, the blue bar from the 60, 70, 80, 90, average those all together to get this blue bar for blade 1. And then we average these 3 blades together to get an average value for the propeller. And this way, we are checking things on a macro scale, a blade scale, but also kind of detailed on the path of the water. So each one of these common radius lines, you know, the 50% is 50%, and that's the same water flow each blade is seeing. We want those to be as close as possible, not just the macro level of the blade. And of course, there's even another layer beyond those section pitches. So each one of those individual lines on each blade, from the trailing edge to the leading edge, we can break that up into 3 individual measurements. And that helps us control the local shape of the propeller face. So instead of just looking kind of at the height of the edges, we're looking at how the curvature of the blade changes in 3, 4, or 5 positions. The number of positions is determined by the level, the class level you select. So this is a class 1 here with 3. If we upped it to a class 4, a class S, there would be 4 segments here. And so it starts to get very created as you keep breaking this down deeper and deeper. And again, the higher classes have more measurements and tighter tolerances. And that helps keep the shape of the blades very similar from blade to blade to blade. So is there more to the story? The answer is obviously yes. Pitch is a common characteristic shared by all inspection methods, but pitch is simply the angle of the blade. And we've purposely focused on pitch for this presentation because that's something that a lot of people have been exposed to. But ISO 484 and manufacturers who are actually following this have a lot more to check. If we think about the propeller, what about the spacing between the blades? These blades could all be identical, but let's say two are close together. Mean for performance. So blade spacing is one of the things that's checked. What about the inclination of the blade, the rake angle of the blade? One blade is leaning forward and one blade is leaning back, but they're exactly the same angle. Sorry about that. If one blade is leaning forward and one blade is leaning back, but they're exactly the same angle, what does that mean for performance? So similarly, the outline and the width of the blade, the rotational balance of the blade, all of this should be checked if you're doing a thorough inspection. So yes, there's a lot more to the story, and we've done what we can to advance things and check even more of these criteria depending on the machine's capabilities. Not all machines have the recording capabilities to get all this, but we try to capture as much of this information as we can with our software these days. And that kind of brings us towards the end of the presentation here, where we're going to talk about our mission at TrueProp. And our mission is that we are focused on inspection software and integrations with existing systems. So our flagship product, TrueProp, it's perpetually updated and improved with a few major updates each year. Our software is independent of any specific device. So developing new software and hardware connections is also one of the services we provide. And we're happy to continue to provide options for the industry to maintain and extend the life of their existing devices. We know that these devices are critical to the day-to-day businesses, and we're doing our best to support them. So TrueProp can connect directly to most digital devices, digital pitchometers, and that allows you to acquire and process the scan data. So you acquire it and then you can analyze it and print reports. Now, TrueProp also has a manual data entry and a virtual data extraction, which can be used to pull data out of 3D laser scans. So these are some of the things that we're just continuing to work on here. And you know, we've really just scratched the surface of the world of propeller inspection with this webinar. We really look forward to kind of continuing to reach out to our customers and supporters with more conversations and more in-depth webinars in the future. So with that, we can round out to the outro here. So thank you everyone for your attention. And the last thing I'd like to say is we'll be doing another presentation next week, same time on Thursday, and it's going to be on the virtual inspection of 3D laser scans. So, you know, taking a propeller, scanning that blade, we're not going to actually show that process, but we'll show the data capture, we'll show the data extraction, and what you might be able to do with some of this technology. It's going to be a little bit more of a demo, but it should be really interesting as well. So tune in next week. And with that, we will have Dawn kind of propose some questions here.
Yep. Thanks very much, Adam. Just one comment. We've had a few people report some audio difficulties, and we certainly apologize for that. But this recording or this webinar will be recorded, so you'll be able to get the full screens and audio if you want to refer back to that. We'll be sending you an email with links to all of those. But a couple of the technical questions that came through, one has to do with the ISO 484, the two different parts of it, a part 1 and a part 2, and specifically are the local segment definitions different between those two criteria?
I would have to review explicitly, but yes, there are two, I guess, documents regarding ISO 484, a -1 and a -2, depending on the propeller diameter. And for the smaller subset, for the smaller diameters, there's a minimum value for a lot of things that at some point measurements begin to tolerances based on diameter begin to become so small that they're not very meaningful. So there's a minimums in the small propeller document. Now, in the large propeller documents, there's also an upper limit to the local pitch segment length. And so in some cases with long chord lengths, you can get more segments than just 4 or whatever is specified for the class you're selecting. There are minor differences between those two documents. There's also minor differences between those two documents in which radii positions must be taken for I believe, a class 2. Hopefully that answers that question.
Yep, we had one question about laser scans, but you answered that with the presentation for next week. And we have a question about how to source hardware for this type of propeller inspection. And if I may, let me make a comment to that. TrueProp software was really developed to be an independent source. So we do not, TrueProp software does not endorse, recommend, or really refer any devices just in order to maintain that independent focus. That said, we do work with device manufacturers in an OEM setting. And so if you have any questions about that, yeah, reach out to TrueProp Software personally at measure@truepropsoftware.com. Just it's more appropriate given the mission and the community that is served both with TrueProp software and HydroComp. We try to maintain a sort of the high ground of being an independent source and not really restricted or focused on any one particular supplier of anything, whether that be measurement devices, engines, propellers, gearboxes, whatever.
Yeah, and our true expertise kind of lies in the connection between the computer and the device itself. So, a lot of times people have existing hardware, and so we're very good at being able to make the connection in between. So yeah, email us, let us know what you're working with, and we'll be happy to talk with you.
Great. That's the end of the questions. Great webinar, Adam, as always. On behalf of TrueProp and HydroComp, thank you very much, and we'll look forward to seeing you next week.
Thank you, everyone. Bye.